Alright, so in this video we're going to talk about the ideal gas law. We learned previously that when we are at STP, 1 mole of a gas occupies 22.4 liters. But what happens when we are not at STP? The ideal gas law allows us to calculate the number of moles of gas when we are not at STP, and that's the important piece there. We can also use it when we are at STP, and that's actually how we use the variables together. Alright, so we have our formula, PV equals nRT, and again, this can be found in your reference packet, where again, P stands for pressure, V stands for volume, T stands for temperature, N stands for the moles, and R is what we call our gas constant. Alright, so our volume must be in liters, and our temperature must be in Kelvin. And this has to do with our gas constants and the units that they're in. The other thing that's important is that our pressure unit and our gas constant must match. Right? These units must match. And we'll look at that here in a minute. So, the ideal gas law constant was experimentally determined at STP, and that's how we have to use them. So we have 3 values. They're all found in your reference table. Okay? And again, they are dependent on the units of pressure. So we have 62.4, and that's for millimeters of mercury. So the unit is millimeters of mercury times liters over moles times Kelvin. We also have 0.0821, and that's atmospheres times liters over moles times Kelvin. And then we have 8.31, which is kilopascals times liters over moles times Kelvin. So if we have a problem where we're given pressure in millimeters of mercury, we would have to use this value for R. If we're given our unit of pressure in atmospheres, we would use this one. And if we're given kilopascals, we would use this one. Okay? So let's look at our problem. Calculate the volume that at a 0.323 mole sample of gas will occupy at 265 Kelvin and 0.9 atmospheres. Alright, so what are our variables? We have our volume is unknown. We have moles, which is N, at 0.323 moles. Right? And then we have our temperature, right, which is 265 Kelvin. And then we have our atmospheres, which is a unit of pressure, 0.9 atmospheres. So we need to choose our R value, again, based on our unit of pressure. So since our unit of pressure is atmospheres, our value for R is going to be 0.0821. Again, that's because it's atmospheres in there. Okay. So the equation is PV equals nRT. We want to rearrange to solve for V. Right, I'm going to rearrange to solve for V, so we're just going to divide both sides by P. And that tells us that V is equal to nRT over P. Right, and then we just plug into that. So our volume will be equal to our number of moles, which is 0.323, times our R, we chose 0.0821, and then our temperature, which has to be in Kelvin, right, was given to us as 265. Sorry. And then we're going to divide all of that by our pressure, which was 0.9 atm. Alright, and then we will calculate our volume. So we multiply 0.323 times 0.0821 times 265 and divide by 0.9. And we get 7.0 8. And let's look at our significant figures. We have 3 here, 3 there, 3 there. So we'll round that to 1. Now, what will be the unit? We said earlier that volume has to be in liters, which means liters will come out when we are solving for it. But why is that? So if we look at our problem and all of our units, we'll see we have moles on top, moles on the bottom. That cancels, right? We have Kelvin on the top, Kelvin on the bottom. That cancels. We also have atmospheres on the top and atmospheres on the bottom, so that cancels. So what's left over are liters. And that's how we know what unit we have left over. All right, and so that's it for today.